I would like to explain a little bit about how complex numbers can be used in applications that you're likely to encounter if you intend to become an engineer, particularly an electronics engineer. In electronics, complex numbers are used to represent a phenomenon known as impedance, which is a combination of resistance, the opposition that something offers to direct current, symbolized like that in a diagram, and reactance, which is the opposition that a device or component will offer to alternating current. These two components are entirely separate and independent from each other. In mathematical terms, resistance is denoted as R and is a real number quantity, but reactance is denoted as Jx, and that is an imaginary quantity. If we have inductance, that's a coil like this. Coil is the most common inductor that you will find. Then the reactance is positive imaginary. If, on the other hand, we have a capacitance, then the reactance is negative imaginary. So in the case of an inductor, X is a positive real number, and in the case of a capacitor, X is a negative real number. So we might have a complex impedance, say 3 plus J4. That would be 3 ohms of resistance. That is the unit for resistance and reactance, the ohm, OHM. 3 ohms of resistance and 4 ohms of inductive reactance. If, on the other hand, we were to have a minus sign here rather than a plus sign, that would be 4 ohms of capacitive reactance. Now, reactance for an inductor or a capacitor depends on the alternating current frequency, and I explain all of this in my book, Teach Yourself Electricity and Electronics. And this is in regards to the 5th edition, but in all editions I explain that concept. So you will get plenty of information about that if you go and refer to that book. Okay, so let's check an actual example of what we might see when we connect a capacitor and a resistor in series. Then we'll look at what happens if we connect an inductor and a resistor in series. This is called an RC circuit, resistance capacitance. This is called an RL circuit. Now, C means capacitance, X means reactance. Don't get that confused. The capacitance and the reactance are two entirely different things. L stands for inductance or inductor. So this is an RL circuit. Let's just suppose that here we have minus J5 and here we have 7. 7 ohms of resistance and minus J5 imaginary capacitive reactance. Now here let's suppose that we have, on the other hand, J2. And we can put a plus sign in front of that for now to indicate that that is inductive reactance. And let's just say we have 3 ohms of resistance here. What's going to happen if we connect this entire circuit all together in series? That is, if we move this so that it's in series like that with this. What's going to happen? What are we going to get? We're going to get a new impedance, and this is what this combination of resistance and reactance is. That's what impedance is. So we add the real number parts and we get 7 plus 3 is 10 ohms of resistance. We add the imaginary parts, we get minus J5 plus J2, so that's minus J3. So if we connect all 4 of these components in series in any sequence whatsoever, we're going to get the equivalent impedance, symbolized Z, of 10 minus J3. That's going to be the complex impedance. When we connect components in series, their resistance components add and their reactance components add, and it's just straightforward complex arithmetic, complex number addition. So that is an example of how these components work when we connect them in series. Now, if we connect them in parallel, the situation becomes completely different, and I will warn you ahead of time, a good deal more complicated. But we're not going to go into that right now. We're simply going to stick with this, and you can remember how that works.